Hello everyone, my name is Thanh Bui from Aalto University. Today I'm going to talk about a new class of attack. We call it Man as a Machine, and I will show how to perform this attack on security critical applications, including password manager and security tokens. So we see software with client and server architecture everywhere. Let's take browser and web server for example. In traditional network threat model, the user device and the server are typically trusted, but the network is hostile. The attacker can do various types of attacks, like man in the middle, to steal user information on this channel. Because we are aware of this attack, we use crypto solutions such as TLS and the Web PKI to protect the communication. However, not all communication goes over the network. Certain part of the communication happens within the computer. For example, software often comprises of front end that provides the GUI to the user and the back end that manages the data. They are separate processes and they use a mechanism called inter-process communication to exchange data. Because there can be untrusted components inside the user device, and protecting user information communicated over the channel is as important as over the network. So for this reason, in this work, we try to understand the security of the communication inside the computer with focusing on IPC security. We call the attacker that exploits the inter-process communication inside the computer man in the machine. And let's see who is it man the machine. So we consider the threats from malicious processes on the user device. However, we are not interested in malware because malware usually run with at the same user's permission. So if the computer is infected by the malware, then nothing we can do here. So instead, we are interested in legitimate processes that run by other users. These processes are intended to be on the computer. So in our threat model, the attacker can be any unprivileged user that tries to steal sensitive information from other users on the same computer. The example here includes coworker, family member, and even the guest user. The target system here is multi-user computers. Computers that can be accessed by multiple users are very common. Think of enterprises or university where centralized access control is used to allow any employee or student to access any computers. In such environment, even though everyone has their own computers, but they can be accessed by any other domain users with their own credentials. We also found that the attacker can also be guest user. Many operating systems, such as Ubuntu, they enable get access by default, and even security practitioners usually forget to turn this off. So the attacker here could be anyone, not just insiders. Let's take a look at the figure here, and I will show how the Mitma attacker to attack other users on the same computer. The attack method is to run a malicious process from the attacker's login sessions. An example of such attack scenario is the attacker first signs into the victim's computer and runs the evil process. After that, he uses fast user switching on Windows to leave the session in the background and switch back to the victim's login screen. So this way, the background sessions continue to run in the continue to have the attacker's process, and this process will try to exploit the victim's process's IPC. On Mac OS and Linux, commands like no-hop can be used to keep a process running in the background without leaving the login sessions. Things could be worse if remote desktop like SSH or remote access like SSH or remote desktop on Windows enabled on the computer. With these, the attacker could start the evil process from remotely. So there are many types of IPC, and not all of them are vulnerable to the Mitma attack model. The common feature of the vulnerable IPC methods is that the server process binds to an identifier or name and waits for client connections. In this work, we focus on three IPC methods: network socket, where the server listens on the localhost interface and a specific port number; namepipe on Windows, where the pipe instances are stored in a special path where all users can access. As I will show later, the Mitma attacker could perform client and server impersonation on these IPC channels. The third IPC method is USB human interface device. Strictly speaking, USB is not an IPC, but USB communication happens inside the computer, leaving the Mitma attacker to exploit it. Examples of USB HID devices are security key that many people use for second-factor authentication. On Linux and macOS, only the current active user can access these devices. However, on Windows, any user can access this device at any time. There are also IPC methods that are secure against our attacker model, such as socket pair or anonymous pipe. The difference here is that both of the communication points of this IPC are created by the same process. This way, an untrusted process cannot get into the middle and exploit this channel. Now I will show how we can exploit this IPC method in password manager and security tokens. Our primary case study is standalone password managers. They are different from cloud password manager like LastPass in the sense that they provide a native desktop app that allows users to manage the passwords. Standalone password managers are often integrated into browser with browser extension. This browser extension helps users in entering password into login pages or storing the password. The browser extension and the app communicate the password and other user information over IPC. In this work, we analyze various password managers to see how they protect this channel. The first case study I would like to talk about is RoboForm. The RoboForm app runs an HTTP server on port 54512 and waits for client connection. The RoboForm browser extension connects as a client to the server and queries the password from the app. The problem here is that there is no authentication on the IPC channel between the browser extension and the server. The app will respond to any client without verifying if it is actually the legitimate browser extension. So it's quite easy for the Mitma attacker to exploit RoboForm. The attacker is an unprivileged user that's running malicious process in the background, so he can perform client impersonation here just by connecting as a client to the server's app, to the app server, and query the whole password database from the app. So now let's take a look at more complex example. So 1Password is another popular password manager. This case is more interesting because the developer tries to protect the IPC channel between the browser extension and the app, but it's not good enough to defend against the Mitma attacker. Here, the app runs a WebSocket server on port 6263 and waits for connection from the browser extension. When the server got the connection, it verifies the client very carefully. It checks the browser extension ID on the HTTP header of each request. It also checks the code sending signature of the client process to make sure that it is a known browser. And most importantly, the server checks whether the server and the client processes are owned by the same user. So with this check, we couldn't perform client impersonation as in case of RoboForm. However, the client doesn't verify the server. It actually cannot because the browser extension is sandboxed by the browser, so it has access to very limited APIs. So this allows the Mitma attacker to perform server impersonation. And even though the client and server run an ad hoc protocol in the first communication to derive a shared encryption key, the design of this protocol is not secure, and it's not secure enough to prevent the server impersonation attack. Now I will show the protocol. The client here is a browser extension, and the server is a desktop. So you can see here that this is clearly not a secure protocol. All of the material of the final key are sent in the messages. And if you can take a look at step 4 and 5, the user confirmation only happened on the server side. So it means that a malicious server can just skip this confirmation. So this insecure protocol, together with the fact that there's no server verification, allows the Mitma attacker to perform server impersonation on one password. And this is how the Mitma attacker can do the attack. So first, the attacker just needs to run a WebSocket server on port 6263 before the desktop app does it. And when the app tries to run the server and see that the port has been taken, the app just fails silently without informing the user. And when the attacker server got connection from the browser extension, it does the key derivation protocol that I showed before, and it just keeps user confirmation. Unlike RoboForm, the Mitma attacker here cannot access the password database, but we found that he can send a command called collect document to the browser extension and collect all the data that the victim enters into web forms, including login credentials. The third case study I would like to talk about is FIDO U2F security key. So FIDO U2F is a standard for second authentication factor, and it is supported by many popular services such as Google, Facebook, and GitHub. And most security keys implement this standard, including YubiKey, and even the new Titan security key that Google introduced a few weeks ago also follows this standard. As you can see on the right is a simplified protocol of how the U2F security works. So first, the user must register the device with the online service that it wants to enable second factor authentication. Basically here, the device generates a public key pair, and the service links the public key with the user. After that, when the user wants to log into the service will send a challenge to the browser and expect to see a response that containing the device signature on the challenge. To get the response, the browser will keep sending the challenge to the device until we get the response. However, the device doesn't automatically sign any request that it receives. It needs to be activated by touching a button on it, and it only responds to only the first request that it received after the touch. Now we show how the Mitma attacker could exploit U2F security keys. So since the security keys is supposed to prevent malicious login even when the user password has been compromised, we assume here that the attacker has obtained the victim's password and now trying to crack the second factor. The attacker will exploit the fact that on Windows, any users, even the one in the background, can access the USB HID devices at any time. The attack is as follows. So first, the attacker runs malicious browser process in his login sessions and signs into the service using the username and password he has obtained. The malicious browser will receive a challenge from the service. After that, the malicious browser will keep sending the challenge to the device at a higher rate than a legitimate browser would do to increase the chance of getting that challenge side. This is easy because, for example, Chrome only sends a challenge to the device every 300 milliseconds. When the victim signs into any service using the same security key, the victim would touch the button on the device. And because the attacker is sending the challenge to the device at a very high rate, the attacker will get his request signed with very high probability because it is sent with higher rate than the legitimate browser. The user might notice that the first button touch has no effect because it is used by the attacker, but such glitches are common in computers and typically ignored. We tested the attack on popular services, including Facebook and GitHub, and we got 100% success rate. So we have seen how we exploited RoboForm, 1Password, and FIDO U2F key. But those are not all the applications that we found vulnerable to Mitma attacker. This is a list of apps and their vulnerabilities that we found. Password manager and login credentials are our main focus. We also found vulnerabilities in other apps that follow client and server architecture. For example, in the case of MySQL, if client and the server are on the same computer, the client can connect to the server using name pipe, and we were able to perform man-in-the-middle attack on this channel to obtain all the queries and query results on this channel. So how can the Mitma attack be mitigated? So since the attack are performed by leaving a malicious process running in the background, the most straightforward solution would be to limit the number of users that have access to the computer. Ideally, each computer should only be accessed by only one user. And remote access should also be disabled or limited to only one user. The Mitma attack can also easily be detected. The application developer can simply compare the owner of the client and the server processes, and if they are owned by the same user, then he can be sure that the channel cannot be exploited by the Mitma attacker. It might be more difficult for a JavaScript client running in web browser, such as browser extension, because they don't have access to the operating system API to do the owner check. In this case, cryptographic solutions such as user-assisted pairing protocol or even TLS can be used to protect IPC communication. So the main takeaway message from this presentation is that IPC is not inherently secure. There has been a common belief that there's nothing we can do to defend against local attacker. It may be true if the user device is infected by malware. However, as we have seen, there are many other potential attackers. Any user, regardless of their privileges, including guests, can attack IPC of other users on the same computer. And unlike malware, developers can totally defend the application against this type of attacker. And this concludes my presentation. Thank you for attention. Any questions?
Questions?
Hello, I'm Jeffrey Goldberg from 1Password. I'm the one who did that ad hoc week broken protocol there. So first of all, I want to thank you for this paper. It's outstanding, and we had not considered user-assisted key exchange, which would have solved the problem. But for anybody who's interested in why we had the lousy key exchange in there, either talk to me or I've posted a link. I've tweeted a link to a discussion of that.
Thank you.
Thanks. And never let it said that academic research doesn't affect the real world. Any other questions? Come on, people.
think it's more like a comment. My name is Samuel Weiser at Graz University of Technology. I would say U2F is not insecure in terms of the protocol, but it's more like an issue of secure output, presenting something to the user so that the user can know which challenge he's signing right now.
So here we think that it's not really the problem of the U2F protocol, but it's more like the problem of Windows. So Windows shouldn't allow U2F, should allow USB XID devices to be accessed by any users at the same time.
Yeah, I think there's still other attacks possible if you constrain this to a certain browser only, like in-browser separate sessions in the same browser.
Maybe we can talk later.
Okay.
Hi, Matthew Elder, Johns Hopkins Applied Physics Laboratory. Really interesting work, good work. Did you notify the vendors? Did they give responses? Besides the one, I mean, you had a list of, there was like 10, 12, okay.
Yes, we did notify all of them.
Are they fixing them, or?
Yeah, most of them has fixed problem.
Okay, thank you.